Hi, today is the first review class for final exam. I looked at the test we took, we're still grading it. Okay. Well, I'm afraid of half of still couldn't pass the second test. Okay. We still have no idea what is a proof for the convergence, divergence. That's what I'm all about. Okay, so the proof, what is called a proof for the divergence converging. Now, sometimes the answer is correct. The sequence, the series is convergent, but you have to use the right argument to prove it. A typical example is the one sine n over n squared. Okay, so I'm beginning with that problem. I just want to talk about what is, why you couldn't get 4 credits even you prove this is a convergent. Okay, of course, few students say it's divergent. Okay. So this is a question. Okay, check. Yeah. Prove it's convergent. Now, how do you prove it? Okay. More, among those who get correct answer, I say it's convergent, right? And the proof, I only saw a couple of them, the proof is perfect, correct. The rest of them, they're wrong. Number one is, when you use a comparison test, there was assumption there. Comparison test, you forgot the assumption. Every test, there was a condition that all the term must be positive. Otherwise, you cannot compare, okay? And if you understand the proof, then you remember this must be hard. But if you don't understand the proof of the comparison test, then you will forget those assumptions, conditions, okay? So, yes, sine n is less than 1 or equal to 1, saying sine is between positive and negative 1. So here's the argument, typical argument. Sine n is less than equal 1. Okay? Therefore, sine n over n squared less than equal to n squared. So the one on the right hand side is convergent, implies the one on the right hand side is convergent. No, that's wrong. Why? Because this series does not satisfy the condition for the comparison test. The comparison test says that if you have 2 series, A and B and both are positive or no negative, if n is less than or equal to Bn and the Bn, you see, let's recall why we needed that positivity, right? So you have so this is you have 2 series, but there's assumption, okay? Assumption, you probably never pay attention, n greater than or equal to 0, Bn greater than or equal to 0. Then if n is less than or equal to Bn, then this should be less than or equal to. The reason is the series is always either convergent or finite. Either convergent to a finite number or infinity. So that's the reason I can always put there. Then if the other one is negative, only under that condition, you have this. So if the one on the right hand side is finite, then implies the one on the left hand side is finite. Okay, why? Because left hand side actually is greater than or equal to 0, right? So if we have a number, even you see, if n, you don't know the sign. If you don't know the sign, then you may still have this, as long as it's convergent. Okay, this is a finite, but does not imply this is a finite. It's logic. It could be negative infinity, right? There's no lower bound there. That's the point. Even it's convergent, does not even it's convergent to even sometimes the limit doesn't exist. Even the limit is the infinity or a finite number. Yeah, if the limit okay, I should have said this inequality holds as long as both limits exist. But the one on the left hand side could be negative infinity. It still meets that requirement. So only So there is assumption here. Okay, and if the another important fact, you know that if n is greater than or equal to 0, then this one starts from n in n, right? It only have two cases, either infinity or a finite number. Okay, in other words, the limit, i.e., the limit n approaches infinity, this one always exists in the sense, could be infinity, could be finite, right? Yeah, always exists in the sense that infinity or finite number or some L, okay? Finite number, okay? But this is not true for a series when n is not a changing signs. Okay? Sometimes the limit itself does not exist, does not go to infinity or go to finite number. So you have to be careful about that. All right, so because it does not, sine n over n squared does not satisfy the condition set for the comparison test, you cannot apply the comparison test directly. Okay? So what do you have to do? Okay, we even don't know whether the limit exists, right? So what you do is you have to use sine n, it's less than or equal to 1, right? That's okay. Therefore, okay, therefore, your an is going to be sine n over n squared, right? So sigma this one, okay, every term is positive, non-negative, right? So this is going to be, yeah, this is actually, you can apply the comparison test to this series, not to the original series, because now absolute of n is always greater than or equal to 0, right? Then since n is less than or equal to n squared, which is bn, right? Now you can apply the comparison test because absolute of n is non-negative, right? So this is in this case, since okay, is convergent by the B series test. Okay, we conclude that we see that sigma, not n, this one is convergent. Okay, by the comparison test. So all the tests in the book, when you apply that, you have to verify those conditions. Okay, you cannot just memorize the final statement of the test. Okay, then this implies this is convergent. Actually, it's absolutely convergent. Right? Okay. Okay. Then this is a complete. So I took 2 points off if you did not do that way to prove prove this is convergent. Okay, you did not you apply the comparison test directly to the original series. It seems that's right. Okay, so the reality here is if there was no quiz, more than half the students did not attend the classes. Okay, in other sections, some professors always count the attendance every time. And I say I didn't want to do that. That's just a waste of time because everybody's an adult. It's not students in elementary school. You pay the tuition, so that's up to you. But something overestimate his ability to study the material or my lecture notes or the book. Right? If you are able to do it, no problem. But only the student who has a PhD in general has this ability. Without attending classes, can read the book and still get an A. That's my general observation. Not everybody. When I was a student, I had many good teachers, so I didn't even read the books. Okay, and so when I get in graduate school, you know what? I was so frustrated because the teacher did not teach all the details. So I had to read the book. It's very hard at the very beginning. Okay, so I don't think students, majority of students in calculus, have this ability to read the math book and do the homework, and still can get A. That's so. Attending classes, it's always you probably did not see that, but it's easy to understand the material when you get home to read it. And sometimes we emphasize some points which is not clearly mentioned in the book. Like today, if you really have to check the conditions for each test before you apply it. Okay. And each test, you see, if the test does not say if and only if, then you cannot. If the test only says that under this condition, under this inequality, well, if this inequality holds, then it's convergent. But does not mean if this inequality is not satisfying, then it's divergent. It's a logic, only that's necessary does not mean sufficient. So they're not equivalent. You cannot use that to prove convergence. Like the nth term test, like a test for divergence. I call it test divergence instead of nth term test is because that's only works for divergence, to prove divergence. So if n the limit of n is not equal to 0, then this is divergent. But if it is equal to 0, I never said that's convergent, right? So you cannot use that to prove it's convergent, right? That's only works for the divergence. So another typical example in the test, I think more than half the students couldn't do the problem when I was grading. And this is a so simple problem. We did it in the class many times, not just one, okay? n+1 or n, it doesn't matter. Okay? Look at this, it's obvious it's divergent. There's some students say it's convergent, and some students even using ratio test, because this is a very powerful test. I always use it for every problem. Ratio test. The ratio test, yes, you can use a ratio test, but the limit is 1, because those are the polynomials, right? Numerator is polynomial, denominator is 1. So you never get something different, just must be 1. And the ratio test clearly says that if L equals 1, inconclusive. Only when it's less than 1, it's positive, it's convergent, and greater than 1, it's divergent. If you look at my solutions to test 2, yeah, there was a problem like n times e to the negative n, something like that, right? Unfortunately, about 20% of the students did not get the correct conclusion just because mistakes in the computation. When they're simplifying, use a ratio test, instead of get the 1 over e, some got 0, some got infinity, all kinds of limits. And I'm very surprised, like even n plus 1 over n, the limit will be 0. Then it's hard, I did not take too much point because this is already get a correct idea, just cannot, find the limit. Okay? Yes.
So you say that half of the class did not pass test 2?
So, based on what I'm grading, I'm feeling like that, because the second, third pages, the proofs is sometimes either nothing there, or it's there but I cannot get full credits, and many arguments is totally wrong. Yes. I don't know. I just post my solutions. It really doesn't matter. Just look at my solutions. Okay, you can see how many points you are going to get. Okay. Okay. So I just grade half of them. Okay, not done yet. Okay. So look at this one. Why it's convergent? Why it is divergent? Because if it is convergent, the nth term converging to 0. But look at the n minus 1 over n plus 1. It does not, right? This is going to be 1. So it's not going to be 0, but this is not the origin term, right? This implies this one does not exist. Okay, it's not going to be 1, it's not going to be negative 1. You can, a couple of students use like an n takes even term, n takes odd numbers, and you get different. That's okay. But then you don't need to say so much. It clearly does not exist. Because when n is even, and this approaches positive 1, when n is odd numbers, it approaches negative 1, then you still conclude that the limit doesn't exist. So you can short the argument and just say clearly it does not exist. That's enough. But you have to point out that. Right? Of course, it does not exist. Of course, the limit is not going to be 0 because it does not exist. Right? No existence. How can you say it's 0, right? So this, if we really want to put more details, I have to say that this is not going to be 0. That's a true statement. Because the left-hand side doesn't exist. Of course, it's not going to be 0 at all, right? Then this implies this series is divergent, okay? By whatever, by the test for divergence or by the instant test. But it's very clear, the last statement by the test for divergence. Okay, so those are the two examples I want to talk about. Yeah, I'm going to use a example final exam 5 to discuss and look at this problem. I'm not going to discuss all the problems today. That would be not the first. That's not enough time. But I want to focus on those series problems. Okay, because this is much hard problems. Yes. Okay. There's another type of problems. I still have to say more than 50 students still don't know how to do it. No matter how many times I find the power series representation for the you have to understand that before the final exam. Otherwise, you're not going to do well because 10 points for that problem. Okay. So this is a question like f of x equals 3 minus 2x. Okay, and to find the power series representation for the function I already clearly state that the power series representation must be in the form x minus 1 or x minus 2, doesn't matter. Okay? I can put any number there. Okay? Let's just choose x minus 1 to the power n. So clearly, it's already said it must be in that form. But then there are certain number of students still don't give me a different form. You didn't even look at the problem. That's the issue. You have to look at the problem, right? The question, it's in that form, x minus 1. That means this is a power series at 1. Right? It's not x to the power n. Okay, so read the question carefully. Power series representation is in that form. Very few students have learned this skill to get that quickly. Okay, okay, because eventually you're going to that. But what you know is something like this, right? Yeah, that's okay. So majority of students know this formula. The question is how to use it, right? How to use it, right? So you have to express. So in the place of x here, it should be x minus 1. So you have to express that function in that form 1 minus x, right? Something like that. So what it is, this will be x minus 1 plus 1. Okay, this is the part I needed, right? X minus 1. So this is going to be, let's put a u plus 1 here. Right? U is x minus 1. Then f of x This will be x, this is u plus 1. Now, there are few students learn this technique, okay? Not few. Honestly, I have to say few. Even among the few, half of them still couldn't make it to the end. Why? Because of computation mistakes. You know, when you remove the parenthesis, whoops, you know, you get totally different things, right? If you remove the parenthesis, and you will get 3 minus 2u, minus 2, right? So just step by step. Actually, now you get 1 minus 2u. So it's very similar to 1 over 1 minus x. So if you use that formula to here, right? X should be equal to 2u. Clear? Yeah, x should be equal to 2u. Right? Yeah, then you replace it. So it's going to be 2u to the power n. Right? So then you get to the n, and u is the x minus 1 to the n. Okay? Now, it holds when 2u is less than 1. It's equivalent to say when x minus 1 is less than or equal to 1 half. Okay. That's it. We just needed to use the well-known result to modify that. Okay. Okay. And I just realized that the Taylor series, the last one, is very similar to the bonus problem in example number 5. Okay. So in example number 5, there is a bonus problem. Find the Taylor series for the function f of x equal e to the 3x at a equals 1. Okay, but the one on the test is e to the negative 3x, remember, right? And I don't know, it's 1, not 2, so I forgot. Yeah. But anyway, so this is a Taylor series. So there are a couple ways to do. One is use a definition. Yes, there are some students use a definition to find a Taylor series. Yeah. So use a definition, then by definition, the Taylor series is going to be this form, right? And the a equals 1. So you have to find all the derivatives and plug in, evaluate the 1. So that's the motivation. So you have f comma x equals 3e to the 3x, right? And then quickly get the general formula, right? So the nth order you will get is going to be 3 to the power n e to the 3x. Okay, so very simple if you know that, right? It's going to be n factorial f of 1, right? So you see f of n 1 is going to be 3 to the n e cubed. Okay, so that's why it's 3 to the n e cubed and x minus 1 cubed. Now n to the power n. Okay, so that this is power series. Now, there was one student, when he expressed his answer, he will say that f of x equal that. Then I think that would be too much. Why? You haven't proved that f of x equal that. How can you claim it's equal this? Equality means both sides are equal, right? You have to take extra time to prove they're equal, but it's not required. Okay, we already I already said that you don't need to prove, so you cannot claim they're equal. So use the definition of a Taylor series. Okay, to find a Taylor series, you cannot claim they're equal unless you want to unless you prove it. Of course, it's more likely it's going to be equal, but maybe they're equal on certain interval, not on the whole, line. It's possible, right? So there are more issues. So you cannot just say equal. Okay, if you put the equal, then you give me the sign. You don't understand the material fully. Understand even if you solve the problem. Okay, you only understand 90% of the material of that section. Okay. Okay, so in mathematics, don't abuse the notation equal. When you put an equal, means those sides equal. Does not mean from left side I can get a right hand side. There's something put the equal. Then ask him what does it mean equality. Do you mean they're equal? No. So where did he learn this? Equality does not mean equal, right? They're equal, right? So don't put equality there. So this is the answer. It's called Taylor series. Right? Now, if you use the well-known result, okay, using the well-known result, then this is equal. Okay, this is equal. Right? This is equal for any x. For any x, this means. Okay, we already proved that. It's in the book. I actually, when I was teaching Taylor series, I already proved that equal. So you don't need to worry about it. You can accept it, you can use it. Anything in that table 1 on page 808. Okay, so you can use that. Then e to the 3x will be e to the 3x is just replace x by 3x. Very simple. If it's e to the negative 2x, no, it's not good. Okay, that's for the Maclaurin series for what? At 0. Okay, this is not Taylor series what I require. Remember, so you cannot stop there. Okay, this is a Taylor series. 3 to the n, x to the n factorial. Okay, but that Taylor series at a equals 0, not a equals 1. Right. So what I have to do is you have to modify it. So x is x minus 1 plus 1, which is u plus 1. Okay, it's the same trick. Please learn that. If you don't learn this, you're going to miss one problem on the final exam. Sure. Okay. Positive infinity, yeah. So that means no condition on that. Then, of course, any number is finite. Okay. Yeah. But the radius convergence is infinity, Okay. All right. So e to the 3x is going to be e to the 3u plus 1, and be careful about that computation. Right. You got an idea, but when you simplify it, right, you get 3u plus 3. Okay, so it's going to be e cubed, then e3u. Then you apply the above formula, n factorial 3u to the power n. Right? Then you multiply this out, e cubed and 3 to the power n. And what the u? U is x minus 1 to the power n. Then you get a power series representation for the function, and this equality e to the 3x equal that. Not only got power series, not only got the Taylor series, I also, I also show that they're equal, right, for any x. So this was a bonus problem, and the last on the sample finding exam. The sample finding exam was the previous finding exam. Okay, one of them. Okay. The test problem, look at sample finding exam 14. Sample finding exam number 5, the problem number 14. This is a problem I put it on test number 2. So there are limited problems there. We don't create it, right? Now this is a slightly different problem. It's similar. Okay, number 14. Okay. Determine whether this series is absolutely convergent or condition convergent or divergent. Okay. So the question is absolutely convergent, conditionally convergent, or divergent, and prove your statement. All right. No bigger difference for this. All right. Sign and change signs. This is not alternating series test. Alternating series at all by definition. Even there is -1 to the power n. But the sine n over n squared, remember, okay, alternating series test, if you use it, okay, if you use it, alternating series test, the Bn must be positive. That, yeah, you cannot forget, you should memorize those assumptions. But the Bn is not positive always. Sine n could be negative. It's so it is, I should say, it is not an alternate series. Right? So you cannot even apply alternating series test to this problem at all. Right. And actually, it's absolutely convergent. Okay? The reason is -1 sine n over n squared is going to be less than or equal to, it's less than or equal to n squared. It's obvious. Okay? So by the you can use a comparison. Right now, this part is always non-negative. So that's the reason this one, okay? And so I get this is a convergent, okay? By the comparison test. Okay? Sigma 1 when the square is convergent, it's obvious. I skip that part of it, but that's clear. All right, then you can say that since this is convergent, then you can say that this series is absolutely convergent. Okay, that's just a couple lines. You can apply the ratio test and the row test only when you see an exponential function or n factorial there. Okay, that only works for that method, for this type of series. So if you see something like that, n squared plus 1, you don't see n factorial, you don't see exponential function, n squared is not an exponential function. So in that case, don't even try to use it. It's inconclusive. If you have to do that, that was the students always use a ratio test for all the problems. Okay, it doesn't work. Okay, and the more complicated, you cannot find the limit. If you want, now this is n, okay? If you try, right, what do you get? I guarantee this approaches 1, okay? This approaches 1 as n approaches infinity, and this inconclusive. Inconclusive. conclusive by the ratio test. Right?
You do the root test?
No, I said many times. Because the limit is 1. Okay, if you use a ratio test to get a limit of 1, and a 99% chance if you use a load test to still get a 1. Okay, the limit still will be 1. Okay, if you can find a limit, more likely it will be 1. Okay, so this is those two methods only work for terms containing n factorial and power function, exponential function. Okay. Okay, inconclusive. So you have to use a ratio limited comparison test because both are polynomials, numerator and denominator, right? N equals n squared plus 1. This one, because it's plus 1, it's clearly, right? But that still does not work. Why? If you use a comparison test, it's not working. The reason is, first of all, this is greater than 0, okay, no problem. The reason is this will be Bn, right? And start from 1 to infinity. But this one is divergent. But they're divergent. So from this argument, you cannot conclude the series of n is finite. Because it's less than or equal to infinity, but then what? Right? Only when the right-hand side is finite, then you can say the left-hand side is finite. So comparison test does not work. Direct. Where's my 5? Okay. Yeah. So the comparison test does not work. Okay. Inconclusive. So you have to use a limited comparison test. N equals n over. I still believe that's about n over n squared, which is 1 over n. Okay, and you can check. You can check n over bn. It's going to be 1. All right, that's enough because 1, as long as this limit is between 0 and 5 infinite. All right, so this is L. So remember, L, as long as L is positive and finite, then they both have the same convergence. Okay, since this goes to infinity, then okay, it's divergent. Okay, so it's divergent by the limited comparison test, right? By the limited comparison test, not the comparison test. Okay. Yeah, we just actually what we did is we actually showed that n is greater than half of the bn. So what is behind that is we use the other property. Okay, you can show that, yeah, something like for large n. So the one on the left hand side is infinity, forces the one on the right hand side infinity. That's for large n. Okay. Yeah, because the n over bn approaches 1, so that's why n is greater than half of the bn for large n. Right, and this one, can you see it's obvious convergent when I give you this problem? Why? Okay, we can, yeah, we can look at these two problems. Okay.
What's the question?
The question is determine the convergence whether it's convergent or divergent, and they give me the reason. Right? It's always the same question. They're all positive. Those you don't need to say it's condition convergent or absolute convergent because they're always positive. Yeah. You cannot apply even it contains power exponential function, but you cannot use ratio test and load test for this particular problem directly. Right? Because root test, how can you deal with the denominator? There's two terms there. Don't make algebraic mistakes. Right? You're not able to, yeah. You know, if you use a root test, right? This is going to be 3, no problem. How about this, right? I put a question mark. So you cannot use a root test. You're not able to simplify the denominator. It's not working. But it's still convergent. The reason it's convergent is like a polynomial. Look at the denominator. 4 to the n is much larger than 3 to the n, right? Okay, so that's it. So all I have to do is to just use the comparison test. Clear? I drop 2 to the n. Then there's a 3 over 4 to the power n, that's a Vn. And as you said, the geometry series, yes. Geometry series test will be used for the Bn, not for the n. Okay, so sigma Bn is convergent since r equals 3 over 4 is less than 1. It's a geometry series, right? And then you can right. So this implies is convergent by the comparison test. We compare, and it's less than or equal to Bn, and Bn is convergent. So sigma Bn is convergent, so sigma Bn is convergent. Yeah. Okay, so this is the best way to do it. Now, how about the other way? When n equals 4 then 2 then plus 3 to the. And you have to go the other way around. I think it's divergent because this one, n itself, 4 to the power n grows much faster than 3 to the power n, even there's a 2 to the power n there. Okay? So what you should do, you have to use the other side, right? So how can you make one smaller? I think you have to replace 2 to the n by 3 to the n. All right? And then that is going to be 4 to the n twice of 3 to the n. That's going to be 1/2 for 3 to the power n. Okay? So you can use a comparison. And this one, this is your Bn. Okay? Now, I think it's obvious. I can use not only need I probably don't need to use a comparison test directly because the limit n approaches infinity Bm is going to be infinity. Okay? Why? Because 4 over 3 is greater than 1. Okay? So that implies, of course, it's not going to be 0. Then by the test, by the divergence, for the test for divergence, this implies sigma n is divergent by the nth term test. Okay. So when you go home, you look at these problems, at least, look at this one. Don't read my solution, because when you read it, you understand does not mean you put in your brain. You have to redo it by yourself, at least. That's the first step to do. If you have a limited time, because you have so many final exams going on, okay? That's the trouble. At the end, it's very difficult to catch up. So my suggestion is just cover my solution, read the problem, and can you do it immediately? Right? And if you understand how to do it, then you're more likely again to, do well on the final exam. Okay? You cover the solution, don't read it. But you still have to read it. That means you're not able to do the same problem if I put it on the final exam. So you have to think about how to improve it quickly. Okay? Yes?
You said we won't be able to do it if I put it on the final exam. Are you sure that?
What do I mean? I said that if you get home, look at the problems we discussed in class. If you don't look at the solution at all, can you recover this proof? Okay? If you cannot, if you still don't want to put extra effort to figure out how to improve it, then you're not. Even I put the exact same problem, just change 3 to 4. You're not able to do it. You cannot remember. You cannot repeat. Yes.
I think we was asking Charles about that. Do you write the final, or is it you working with other?
No, I write the final.
So will it be structured similarly to your test?
Be similar to this final exam. I wrote the test. Yeah. So almost done. I send it to other 4 or 5 instructors, ask them to go through the any errors. Okay. Sometimes, if I print out and do it by myself in my office, usually no error. Sometimes I'm so hungry, but I finish typing, and I just send it to them. Yeah. And usually they suggest that don't like that particular problem, give me the reason and modify it. That's possible. Okay. But the majority of problems will be still there, most. Okay. Yeah. So how do I prepare for the final exam? I look at the previous final exam, the styles should be the same style. And I look at all my the review class notes. Those are my favorite problems I want. Okay. I modify it maybe. Okay. All right. Yeah. Test the series for convergence or divergence. Find the sum if it's convergent. Okay. Yeah, find the sum of its particular. So first of all, this is a geometric series. And I think if it's convergent, I probably even don't need it to find using any other test to prove it's convergent. Okay? Because the geometric series is already know where non-result, you can use it. Okay, it says that okay, this is going to be 1 minus r if r is less than 1. Okay. Yeah. How do you prove that? Is it because 1 plus r squared and so on r to the n? That's going to be 1 minus r, 1 minus 1, right? So if you let n go to infinity, r to the n plus 1 approaches 0. That's why the 1 minus 0, the numerator. Okay. So this is if you let n goes to infinity, right? This side have an infinite term. The right hand side just like that. That's the reason we get the formula. If I is less than 1. Right? Right. So now you can prove that directly or not. You can use that formula, or if you don't want to use a formula, that's 9 over 10 by n start from 1. Be careful, it start from 1, right? So you can do directly. This is going to be, the first term is 9 over 10. So I can take 9 over 10 out. So now I can change the index because n equals 1. So then this will be n start from 0, 1 over 10 to the power n. And then use the above formula. It's going to be 1 over 1 minus 10. Right? Right? I equal 1 over 10. So the answer will be 1. Now, okay. Let's take a look at what does this mean? This means 9 over 10 plus 9 over 10 squared plus 9 over 10 cubed, and keep it going, right? And this is going to be 0.9, 0.09, 0.009, and keep it going, right? And this is going to be 0.99999, right? And we learned this notation in the middle school or elementary school. It denotes 0.9 bar. But this, in calculus, we prove that this is going to be 1. Right? So 0.8 put the bar on top is not going to be 1. But 0.9 put the bar is going to be 1. No difference. Right. Okay. Yeah, there are some other similar problems. We'll probably ask you to do that. It's like -1 to the power n and 2 to the n and divide by to the n, something like that, right? Whether this is convergent, if it's convergent, can you find the sum? Right. If it's convergent, can you get sum? And you have to modify it. What is the sum? Right? Now I may put this problem on the final exam. For example, simple problem. And it would be, I should share that. It would be stupid to use an alternative series test to prove it's convergent. Why? Because you're going to use the geometric series to find the sum directly. You already find the sum. Of course it's convergent, right? Only when it's divergent, you cannot find the sum. You have to prove it's divergent. So it's a waste of time to use alternate series test, but it's convergent. Then you start to find the sum, right? And you already wasted about 5 minutes.
So the last one was convergent.
The
last one was convergent.
Well, it's convergent to what?
And you have used the ratio test? I mean, not the
I just said it's
no, I mean,
it's a geometry series.
right.
Okay, it's already proved the result. You use that.
Right.
Right? You don't need to prove it's convergent. You find the sum already. Of course, it's convergent.
Because the ratio is less than 1.
Yeah, that's right. It's not because of R is less than 1. Absolutely, R is less than 1. Right? There's no if I do not ask you to find the sum, then you probably can use a ratio test to prove it's convergent. Okay? Or use a root test to prove it's convergent. Or you can use, you don't need to prove it's convergent, just find the sum, because that indicates already it's convergent. Find the sum. Okay, we find the sum, right? So there's no need. Like this one, if I just want to test the convergence, test the series for convergence, then yeah. If I do not ask you to find the sum, then you can use all kinds of tests available to you. Yeah, let's list all possible answers. Okay. The first method, alternate series test. Okay. You can use this alternate series. Okay. And it's convergent. Yeah. So Bn equals alternate series test only proves some series convergent. Okay. So you have to show that this is convergent to 0. Then it is convergent by the alternating series test. Okay. Done. Yeah. Yeah, it's obvious. So you don't need to say anything. Okay. Another one is n equals negative n, right? So you can use the ratio test. And for the ratio test, there's absolute value there. Be careful. Okay, you cannot use without absolute value. That means you didn't understand the ratio test. Right. So this is going to be, but there are several students not good in algebra. Whenever you use a ratio test, end up with the wrong limit. Okay, you look at you look at, if you still remember, we did on the test. Yeah, when you simplify something like that, I still remember e to the n times, yeah. That one is convergent, but the limit should be 1 over e. Very few students get that part. Okay, I will talk about that part. So this will be 1 over 2. It's already, the limit is 1/2. It's less than 1. So that implies this is absolutely convergent, not just only convergent. Okay, it's better than the first one. Then use a road test the same. Road test similar. Okay, this is by ratio test. Then also you can use a load test. Okay, similar. Okay, similar ideas. I'm not going to do that. So basically, there are 3 different tests. You can also use a comparison test. Okay, the comparison test says that if n equals, right, then absolute value n is going to be 1 over n, right? So of course it's less than bn. Bn is, right, but the bn is because of geometry series. Okay, so the bn is convergent by the geometric series. I call it test maybe, yeah, because r equals 1/2 is less than 1. Right? So then that implies, but itself it's just geometry series. So this implies it's convergent. then this implies it is absolutely convergent. So this is a simple example, but you can see that there are many arguments you can use. Yeah. But you cannot say n is less than n itself changes sign. You cannot apply the comparison test directly, to the original series because n changes sign. It can be only applied to series with a positive terms. Right? With positive terms. Right. Very last problem. Okay. Find the radius of a convergence. Yeah, find the interval of convergence. Okay. Now, when you look at the power series, it involves exponential function. X to the n is the exponential function for fixed x. So you can use a ratio test, you can row test, doesn't matter. I tell you, it's no big difference. But if you see n factorial, if I change n to n factorial, you have to use a ratio test. Because you cannot figure out, yeah, the nth root of n factorial. But if it's just polynomial there, then the ratio test to row test works very well. So let's use the load test. The load test must be written in the form of absolute value of a. Okay, so it's going to be okay. It's not too bad. The question is how to simplify. The numerator is just x. The denominator. Whoa, how can I deal with this? Yeah. So think about that. Nth root of nth, right? It's going to be. It's not. Be not surprised. Yeah. Let's look at this. Okay. Nth root of square n is going to be square n to the 1/9, right? And that's going to be n to the 1/2 to the 1/9. Then it's clear, right? Okay. Then there's a limit is going to be 1 to the 1/2. Okay. That's it goes to infinity. Okay. We have to use a fact n to the 1/n approach. So that, okay. So this approaches 1/x as n approaches infinity. And clearly, this series is absolutely convergent for x less than 1, divergent if x is greater than 1. So all you needed to do is just look at when x equals 1 or -1. Okay? To save time, when x equals +1, okay, this is a divergent. Why? By the p-series test. P equals 1/2 is less than 1. Okay. When x equals -1, okay, this is a convergent. Why it's convergent? Alternating series test. I don't need to waste the time, by the alternating series test. Okay, alternating series test. So one side is closed, one side is convergent, side is divergent, right? So interval of convergence is going to be -1 to positive. Okay.